Hello there, my name is Charles Msiba. Welcome to another presentation on complex functions. In this presentation, we're going to focus on Taylor and the Mclaren series expansions. Now, our point of departure is, let's say f of z is a complex analytic function, and the higher order derivatives inside and on a closed curve C. Now C is a closed curve. And then let's consider a point z0. And then we know we denote by delta z a change in z. Now, if z0 is a fixed point, then z0 plus change in z is a different point, maybe say close to z0, but with a small change z denoted this way. Now, having this kind of a situation, we can approximate the value of f of z at z0 plus change by this kind of an expression, where f n at z0 denotes the value of the derivative of fz at z0. Now, having this kind of expression, we can consider z to be z plus z0. Now, this expression will be transformed in this way. Now, we note here that if z is equal to z0 plus change in z, this is equivalent to saying change in z is equal to z minus z0. Now, if we substitute this change in z by this expression, in this we obtain a power series like this. And then a power series like this is a power series developed around the particular point or fixed point z0, and the series of this form is going to be called Taylor series expansion. Now, on the other hand, if we consider in this expression z0 to be equal to 0, we obtain a power series expansion of this form. Now z is actually equal to z minus 0, which in this case z0 is replaced by 0, and which means that 0, or the origin, is the center of our development, and this kind of series is going to be called Mclaren series. And we can see that with these coefficients, this series will converge when the absolute value of z is less than 1. Now, we proceed and look at examples of how to develop Taylor series expansion of a given function, like f of z equals to 1 over z squared plus, opening brackets, z plus 1. In this case, we are asked to develop this series around z0 equals to 1, and the options are, we have to do this directly up to 5 terms, and on the other hand, we can use the binomial expansion. Now, at this point here, by directly, Directly means that we must use the derivatives, as you saw. The power series here are defined by means of derivatives divided by the factorials, like 1 factorial, 2 factorial, n factorial, and so on. Now, if we use this definition, where we use derivatives in order to differentiate up to order n, depending on the number of terms we want to go, we say we are finding the power series according to the definition, or we can just say directly. Now, at this point, directly, I would like to give a kind of a warning. A function like this, if we were to differentiate it up to 5 times, is a quotient. We all know that the differentiation is going to be each time complicated by the fact that this is a quotient. So then we need to be very careful when we deal with such functions, and we need to use derivatives. The suggestion here, which addresses the warning we are given, a warning is that a function like this, if we were to handle it using the derivatives as you go higher, order, they're going to get complicated. Now, how do you avoid such complication? The way which I suggest here that you must use to avoid this complication is to try to express this function in terms of its partial fractions. In this case, which means that partial fractions is one of the prerequisite knowledge which you must have thoroughly at your fingertips to be able to handle this type of work. Now, what do we do? What would we do there? Then we take f of z and express f of z in terms of partial fractions. In this case, it should be a over z plus b over z to this for the second time, since z here is a repeated pole, plus c over z plus 1. Now, once we've determined the numerical values of a, b, and c, it will be relatively easy to differentiate this function any times, easier than what it would be when we differentiate this as a quotient. So now we can start on our solution this way. We're finding the power series expansion up to 5 terms in terms of by means of the definition of the power series. Now, what we need to do, we need to express the Taylor series as we are instructed to do. This will be a0 plus a1 z minus 1 to the power 1 plus a2 z minus 1 to the power 2 plus a3 z minus 1 to the power 3 plus, here we note that we've got 1, 2, 3, 4. So our fifth term will be a4 z minus 1 to the power 4, and continues to infinity. Now, we recall that these coefficients are calculated in terms of the derivatives. In this case, what would happen is the an is actually the derivative of f to the power the nth order derivative at, in this case, at z0, which is the center of development, over n factorial. Now, if we talk of the derivative of order 0 here, we're talking about the function itself, then a0 would be equals to the function, which is derivative of order 0 at 1 over 0 factorial, which is 1, so that we get this as the a0. But before we can get to that, we need to sort out the problem of getting a, b, and c. So let's start it this way. We have here f of z equals to 1 over z squared z plus 1 in partial fractions form, a over z plus b over z for the second time plus c over z plus 1. Now, I hope you remember how to do this. We'll get the common denominator here, which is z squared plus z plus 1. Then we divide by z. Here we get z times z plus 1 times a, z times z plus 1 by z, then plus b times z plus 1 plus c z squared. Now, having written this 3 terms as a single fraction like this, we can now compare this right hand side with this fraction here. Since they've got the same common denominator, we can conclude that 1 is equals to a z squared plus a z plus b z plus b plus c z squared. Right here, therefore, 1 is equal to this. Now, grouping, we can have here a plus c z squared plus a plus b z, grouping this 21 over z, plus b, an independent term. Now, comparing the right hand side here, we've got 1 plus, here we've got a linear term, and this side we don't have it, then we can say, consider the coefficient is 0, and we've got a quadratic term here, which here we don't have, and that also is coefficient 0. Now, comparing coefficients on these two expressions, we'll conclude that a plus c is equal to 0, and a plus b is equal to 0, and the b is equals to 1. Now, b is equals to 1. From this equation, we see that a is equal to minus 1. And that also will lead us to conclusion that a is equal to minus c, which therefore c will be equals to minus a, which will be equals to 1. Now we can write our function as f of z equals to minus 1 over z plus 1 over z squared plus 1 over z plus 1. Now obtaining our coefficients, now we would say a0 is equals to f at 1. Why f at 1? Because we saw that the Taylor series, as defined here, the first coefficient, which you can write as a0, is f evaluated at the center of the derivative of the series. The second coefficient is the derivative evaluated at the center of the derivative multiplied by z minus z0. In this case, our z0 was given here as equals to 1. Now, at this stage, now this is a0 will be f at 1. So evaluating f at 1, we substitute, get 1 over 1 plus 1 over 1 squared plus 1 over 1 plus 1, which we get here as minus 1 plus 1 plus half, which gives us half. Now, to get our a1, we need to have the derivative of f of z. So differentiating fz prime. Now, if you look at this expression as it is now, it is easy to differentiate using, in this case, power rule. We can rewrite this expression as minus z to the power minus 1 plus z to the power minus 2 plus z plus 1 to the power minus 1. Differentiating using power rule, we can have the z to the power minus 2 minus 2 z to the power minus 3 and minus z plus 1 to the power minus 2. Now, evaluating this derivative at 1, we have here 1 over 1 squared, which will give us 1, and here we've got 2 over 1 cubed, which will give us 1. Then we've got minus 2, and then here we're going to have 1 over 2 squared, which will give us minus 1 quarter. Now simplifying, we're going to have minus 1, 2, minus 2 plus 1, minus 1, which is give us minus 4 over 4, which is minus 1, minus 1 over 4, which is equal to minus 5 over 4. So now this is our A1, which is equal to minus 5 over 4. Now for our A2, get A2, we need the second derivative, which is the derivative of this. Now we get f second of z equals to minus 2 z minus 3 plus 6 z to the power minus 4 plus 2 brackets z plus 1 to the power minus 3. Now evaluating at term 1, the second derivative, would have here minus 2 over 1 cubed, which is 1, we have minus 2 here. Then here we've got 6 over 1 to the power 4, which is going to give us 6 divided by 1, which is 6. And there we've got plus 2 over 2 to the power 3, which is 8. It is going to give us 4, which is it's going to give us 4 plus 2 over 8, and 4 is 32 over 8 plus 2 over 8, which will give us 34 over 8. Please double check my calculations. I might make some numerical errors here, but you won't look out of that, so that you can correct me wherever I go wrong with my calculations. Now our A2 will be then equals to f second derivative over 2 factorial. So we get here, and we're going to have 34 over 8 divided by 2 factorial, and 2 factorial is 2, so we've got 34 over 8 multiplied by 1 over 2, which will give us 17 over 8. Now I'm going to stop here. I think you've seen what's the process here. We'll continue to find your A3, A4 up to A4. Then you've got your 5 terms. Then writing our power series now, we need to start from our A0 there, which is half, our A1, which is minus 5 over 4, our A2, which is 17 over 8. Then you can write here that Fz is equals to half, always is half, multiplied by Z minus 1, the center of development to the power 0, plus the next coefficient A1 was minus 5 over 4 brackets Z minus 1 to the power 1 plus 17 over 8 multiplied by Z minus 1 to the power 2, and then you must continue there up to 50 terms. Simplifying this, you can simply write as half minus 5 over 4 brackets Z minus 1 plus 17 over 8 Z minus 1 to the power 2. My advice here is you shouldn't worry about writing these terms in decimal numbers. I think they are more accurate if they are written like this. Don't worry about simplifying these different numbers and maybe getting confused with decimal places and all those things. Now, up to there, I think we have developed this power series using the definition. The second part of the exercise required us to use the binomial expansion. I hope you appreciated in this problem how the use of partial fractions simplified our issue of differentiation. Otherwise, at this point, I would like to say thank you for listening. Meet you in the next discussion of the same problem using binomial expansion.